everybody, I'm sure, is familiar with Jen Ellis, who joined us as a faculty member 2 years ago, almost exactly, right? Maybe it was April 1st, April Fool's Day. Not that that says anything, I don't know. But Jen did her bachelor's, master's, and PhD at Guelph. She worked with Jim France on her PhD and did some greenhouse gas modeling that actually is some very highly cited papers in that area in relation to livestock and particularly beef and dairy cattle. She also did a postdoc at Wageningen University, still in association with her PhD advisors and continuing on in that area, and also worked for Trout Nutrition for, I'm not sure exactly how long it was, Jen, but as a modeling scientist with their ag research division. And then we were able to attract her to the university here, still continuing to collaborate with Trout Nutrition and still working on her modeling areas. And so it's really great to have her expertise in the department. We've got this new meta-analysis course, graduate student course, that is very popular and going to be taking up a lot of Jen's time, as it already has. And so today we're very interested to see what her research lab is up to. And so Jen, go ahead and present for us. Thank you.
Awesome. Thank you, John. So in my lab, so we're still a new lab, right? And in preparation for giving the CNM talk, I sat back and thought, and we said, well, actually my lab covers a really diverse group of topics on an array of species using a diverse group of modeling techniques. So, we kind of had a bit of a powwow deciding, okay, what are we going to present and what do we have in common? Really, I think what my lab group has in common is we work with the application of modeling to solve problems and advance our knowledge in animal production systems. So this is kind of the thread of commonality between all of my students. And so what we decided to do today is to actually give my students the opportunity to showcase the research that they're working on, which is in a variety of states of completion because we've only been up and running for 2 years. But essentially, we're going to take you on a bit of a tour to modeling methodologies and how they can be applied to solve problems in animal systems. And so, John mentioned that I started a meta-analysis course. So I've got a couple of my students that are working on meta-analyses, which is really a form of empirical modeling. And so in empirical modeling, we treat the animal as a black, and if it's a cow, black and white box. So we relate inputs to the system or to the model to outputs in terms of performance, right? So we don't really know what's going on inside the animal per se, but we can get some good relationships between what's going in and what's coming out. We also do mechanistic modeling, and this is where we take that black box and we make it fully transparent. So now we're trying to, for example, predict broiler growth, and maybe the feed and the genetics are the inputs, but on the inside of the model, we're really trying to model biologically what's going on. So perhaps we have transactions in that white box that represent metabolic pools or digestion kinetics, things like that. We also have in collaboration been working on some new methodologies that fall within modeling, looking at different machine learning algorithms and how are we going to use these going forward. So everybody's all hyped about big data and machine learning and AI, but when it really boils down to it, how can we use these new modeling methodologies to solve problems and advance our knowledge? So this is kind of what we're going to do today. I'm going to kind of take you on a tour of modeling methods through kind of my graduate students. So hopefully you can see how each of these approaches can be applied to solve practical problems. And so I'm going to pass it off to Vicki Bryson, who is my master's student, and she's going to talk about her project. Go for it, Vicki.
Thanks, Jen. So as Jen mentioned, I'm Vicki Brisson, and I started my master's with Jen in September 2019. I'm using empirical and mechanistic model to study the B vitamin ruminal synthesis and use and the resulting duodenal flow in dairy cows. So why are we interested in looking at B vitamins in dairy cows? B vitamins act as essential coenzymes in protein, lipid, and carbohydrate metabolism. And the latest NRC indicates that the dairy cow's requirements for B vitamin is usually met through their rumen microbiota's ability to synthesize the vitamins, thus resulting in the absence of clinical signs of deficiencies. However, that doesn't mean that their needs are always met, or that the cows aren't suffering from subclinical deficiencies, which could reduce their overall metabolic efficiency. And this gap between requirements and needs has been demonstrated through positive responses to B vitamin supplementation, both dietary and through intramuscular injections, in many studies over the past few years. So the hypotheses that we started out with in this project were that first, B vitamins are heterogeneous molecules that behave differently, and therefore they need to be modeled accordingly. So they can't just be grouped as one whole B vitamin complex. And our second hypothesis was that the duodenal flow of B vitamins can be predicted from the diet chemical composition. The two main objectives of my thesis were first to complete a meta-analysis and generate empirical models that would allow us to describe the effect of diet composition on the B vitamin duodenal flow, but also the impact of changes in ruminal conditions on the rumen microbiota's use and synthesis, which was calculated as the apparent ruminal synthesis of B vitamins. And the second objective I'm now working on is to develop B vitamin mechanistic models that we can incorporate into the existing dairy rumen fermentation model that's been developed by Dr. Jan Dijkstra and his team in 1992. So the database that we're working from to develop these models is comprised of 16 previously published studies by Agriculture and Agri-Food Canada, Michigan State University, and INRA in France, resulting in a total of 325 observations. However, the availability of variables for each observation varies since not all studies reported the same variables. So all of these studies, the diet samples were reanalyzed for B vitamin concentration, as was the duodenal digesta, which represents the amount of B vitamins available for absorption by the cow. And finally, from calculating the difference between the duodenal digesta and the diet concentrations of B vitamins, we represent the apparent ruminal synthesis, which represents the net synthesis and use of vitamins in the rumen. So I'll quickly walk you through the results of our meta-analysis and the best performing empirical models for each B vitamin studied, which included thiamine, riboflavin, niacin, pyridoxine, folates, and cobalamin. I first want to start by highlighting or by mentioning that we included dry matter intake as a scalar variable in all of our linear multivariate models. We also included the B vitamin dietary concentration in all of our models except for cobalamin. And while we did include B vitamin dietary concentration, these B vitamins were only coming from the diet. There was no dietary supplementation of the vitamins. And what we can really notice here is that while there are some similarities between the vitamins, there are also differences. So for instance, we can see that dry matter intake has a negative effect on the apparent ruminal synthesis of thiamine, riboflavin, and pyridoxine, while it has a positive effect on the apparent ruminal synthesis of niacin, folates, and cobalamin. Similarly, we can see that increasing the B vitamin dietary concentration has a negative effect on the apparent ruminal synthesis of thiamine, riboflavin, niacin, and pyridoxine. And finally, the digestible NDF has a negative effect on the apparent ruminal synthesis of riboflavin, niacin, pyridoxine, and folates. And the last thing I want to point out here on our empirical models is that cobalamin behaves quite differently than the other vitamins. And so the best performing model here for cobalamin based on model evaluation indicates a positive effect of both dry matter intake and volatile fatty acid concentration on the apparent ruminal synthesis of cobalamin. And while these can be explained biologically, it does not give us a lot of insight into the actual biological processes that are regulating both the synthesis and use of cobalamin. And that's where we shift towards the use of mechanistic models. So here, this is a theoretical framework for our cobalamin mechanistic model. So to start out, I want to point out that the cobalamin is found within the bacteria of the rumen. And these rumen bacteria are represented by two different pools in the existing dairy models. So first, we've got the amylolytic microbial pool, and then we've got the cellulitic microbial pools. And both of these microbial pools contribute to the synthesis of cobalamin through the inputs of hexose from crude protein and ammonia. And then we've also factored in here for dietary cobalamin supplementation, if that were ever the case, even if that isn't in our current database. And then we've got the proportion of cobalamin that's found within the cellulitic microbes that's shifting towards the amylolytic microbes through engulfment by the protozoa. So we've got the inputs, and then where is this cobalamin going in or going out of? So cobalamin in the rumen is used by the microbes to synthesize propionate. So the cobalamin has the ability to be recycled a number of times for propionate production before it's catabolized. And this number of times it's recycled depends on the propionate production, but also on the cobalamin concentration in the rumen. The remaining cobalamin in the microbes then flows out of the rumen within those bacteria, so either through the liquid or the solid phases. And then the next thing we want to do with these mechanistic models is to develop equations that represent each arrows or fluxes. So if we focus here on the cobalamin associated to the cellulitic microbes, or the breakdown of this cobalamin here, we get this equation. So the first portion of this equation represents that we'd use 1 mole of cobalamin to produce 1 mole of propionate, and then we want to convert those moles into milligrams, which is the unit used to describe all the fluxes and the pools throughout the model. Then the second portion of this equation here just represents the ability of cobalamin to be recycled a number of times. And as I've mentioned previously, this recycling ability depends on the cobalamin concentration in the rumen. So where does this leave us? And what are the next steps that we need to take? So we've only modeled cobalamin, or we've developed a mechanistic model for cobalamin, but we need to develop mechanistic models for the remaining B vitamins. And then our current work has also highlighted the need for further research on the rumen microbiome for a comprehensive understanding of the B vitamin needs. And finally, we'll need to expand the database for further development and validation of our current models. But then you might ask, those models are nice in theory, but how can they be applied to a commercial setting? So these models may be used to determine what rations could require B vitamin supplementation. They may also be used to support precision feeding of B vitamins to high-producing cows. And like other models, the models that we've developed may be used to ensure sustainable farming practices by meeting the dairy cow's B vitamin needs and therefore optimizing the production efficiency. So with that, I want to conclude by thanking our project partners, the Department of Animal Biosciences and Trout Nutrition. And I will pass it over to Anthony, who's also using mechanistic models in another species.
So, hi everyone. My name's Anthony Mirage, and I'm an MSc candidate, and my research focuses on predicting the growth of broilers through the use of mechanistic modeling. So, to start, a little background on how my project came about consumer demand for poultry meat is on the rise. With growing populations, the poultry production facilities must meet the demand of the public. However, as a consequence of this demand, there's also been an increase in demand for slow-growing broilers, as the welfare of these animals is being looked at very closely by the public. Traditionally, grown broilers are known to have a significant amount of health problems as they grow, as they can't keep up with the accelerated growth. These problems include foot pad lesions and breathing problems, amongst other issues. The slow-growing broiler really doesn't suffer from these problems. However, their production value is significantly lower than the traditional broiler. Hence, the development of a broiler model that can predict the growth of the slow-growing broiler and the fast-growing broiler is needed. This can aid producers and academia to deal with the change in demand from the public and improve management protocols based on the data they receive from the model. So, to begin creating this, So to begin creating this model, a previously created model for turkeys was taken from literature to serve as a basis. So here I've kind of outlined what the code for it looks like. In the beginning, you have different packages, and this gives the model different tools to use, as well as identifying constants when you run the program. Things like gender, initial body size, and strain can be edited up here. The second part of the model houses the equations used to represent the different biological processes within the broiler. And then the last part down here contains the code for displaying the results when you actually run the program, such as the graphs and the printable data. Solving of the differential equations are also conducted here as well. So to create that final broiler model, I've outlined 4 steps over my master's thesis to complete it. To begin is changing the exponential kinetics that are within the model. So our first attempt to input some broiler data into the turkey model as it is kind of grinded the model to a halt. This was due to the type of kinetics that the model uses to simulate the different biological processes. We needed to make the model more robust for a range of broiler genetic lines in addition to the turkeys. Therefore, we needed to change it, and I'll talk about those changes in my next slide. But moving on to part 2, which is currently in progress, the goal here is to gather data and develop a reparameterization method to fit the new data to the new kinetics, and also ensure that the new equations can simulate turkey and broiler growth correctly. Part 3 in September 2021 is creating a limiting amino acid routine for the model. So currently the model doesn't have a functioning limiting amino acid routine to reflect that stunting growth when amino acids like methionine and lysine are limited in the diet that the broiler is getting. So upon completion of that, the model will be applied to slow-growing broilers, and quality of life changes to code will commence. This includes, just cleaning up the code, adding result options, and things of that nature. So why change the exponential kinetics that are already in the model? So the original turkey model is originally turkey model that the broiler model is based on runs its equations based on those exponential kinetics that I was talking about. Now, although it can accurately predict parameters during the normal life cycle of turkeys, the model will predict a continuously growing bird. So what this means is that you get a bird of astronomical weight if you run the model for too long of a trial. So in reality, the growth does plateau, which isn't currently being reflected. This has also led to increased computation time problems, and because it has to calculate these big numbers. So to solve this problem, we decided to change them to Michaelis-Menten-based equations, as they more accurately predict the plateau that's seen in reality. And so I've laid out here an example of one of the changes. The equation you see here at the top is the equation used to simulate carcass protein input for a turkey. So Ks in red is the basal protein turnover rate. AIPC/AEPC in yellow reflects age and genetics of protein deposition. And delta CAA in blue reflects the change in feed intake and how that plays in protein carcass deposition. And you'll see this math.exp is representative of Euler's number in Python. So after experimenting with different ways to change the equation, we settled on what is seen below over here. You'll notice that what is underlined in blue is the only thing that has changed and the rest has remained the same. So why is that? When running the code, the delta CAA part of the equation was the only one behaving erratically, and hence it needed to be changed. So the Vmax acts like a cap, becoming the amount of AA that can be used for this action, and allows for easier manipulation of the curve to fit the data. This was repeated for all the equations in the model using delta CAA. So on to what I'm doing right now. So I'm working with Dr. John Kent on a reparameterization routine to apply to the model. We also have an undergraduate student, Rush Carter, developing a database of broiler data from recent literature. Her focus is on studies that include controlled diets and associated growth parameters. So the goal is kind of to finish both at the same time so that the data can be inputted and reparameterization can begin as soon as possible. And with that, the final goal of my master's project is to develop a fully functional broiler model computer program complete with UI. The hope is that it is applicable to undergraduate and graduate courses. Professors and the like can use it to teach students about diets and how different nutrients can affect the growth of birds. Academia and producers can use it to their advantage to test different feed protocols. The code should be easily modifiable, and if anyone in the future wants to include other factors that can affect the growth of broilers, such as temperature stress, that can be easily done. Users should be able to also change the diet, species strain, and the length of the trial to suit their needs. And with that, I'd like to acknowledge the following companies and university, and I'd like to pass the torch to Chris.
Great. Hello, everyone. My name is Christopher Powell. I'm a former postdoc of Jen. Currently, I work at Trow as a ruminant modeling research scientist, but I still spend, 1 day a week roughly working on this project. So today I'm going to talk about Simon, which is the name of the model, which models digestion in veal calves fed milk replacer and solid feeds. In particular, I'm going to be talking about the amino acid routine and how it handles eliminating amino acids and amino acid oxidation and protein synthesis. Perfect. Right, so a little bit about Simon. This is a very large model. It's been around for 20 years, roughly. It started in 1997 from Walter Gerrits's PhD at Wageningen University in the Netherlands. This is a pre-ruminant model, so it's only being fed milk replacer, and it simulated growth based on that. And so the milk replacer was actually put into the model on a continuous basis. But this is for veal calves, and so in Europe there was a recent directive, well, semi-recent directive, saying for welfare issues, we can't just feed these veal calves pure milk replacer. They must be offered solid feeds as well. So given this, we had to update the model to include a rumen fermentation aspect. So this is based off the work of Jan Dijkstra. You're going to hear his name a lot through these presentations. In the early 90s, this was made for dairy cows, and then Jennifer modified this model in 2014 for beef cattle, and then again it's been modified for veal. And so this is a fairly standard rumen fermentation model. We have degradation parameters for the individual feedstuffs. We have retention times, things like that, which drive the microbial population, the degradability of the feedstuffs producing VFAs that can be absorbed via the rumen or the small intestine and things of that nature. One of the really cool things that I liked about the most recent version of Simon is instead of having, a continuous milk replacer meal, whereby I would say, we're feeding, for example, 2,000 grams per day on a continuous basis, we also implemented milk feeding patterns. So you can actually now simulate, if we're going to feed 2 milk replacers a day, 4, 3, whatever you want. And so if you're feeding 2 milk replacer days, for example, in this graph to the left, we can simulate 15-minute meals. And so within the 2 days, the 2 meals in that 1 day, we're going to have full intake in 2 15-minute periods. We can also do the same thing for 4 days, 4 meals a day, for example. We're still feeding the same amount, but over 4 different meals. And this really, it's really nice because it kind of throws like a wrench into the model. So we generally had a steady state model. Now we really have a quasi semi state where we have these huge influxes of nutrients through these milk replacement meals, and we can see how the model reacts to this. And it's really nice just to simulate, within day kinetics and things of that nature. So in terms of this amino acid routine, the barrel theory is very widespread in classical nutrition, pretty much saying that if we have a limiting amino acid, that really sets the maximum for protein synthesis, and if we have other amino acids which are above the level of this limited amino acid, it's not going to increase protein synthesis anymore. It's going to be oxidized instead. So we try to really kind of simulate or mimic this barrel theory in a model. So we did this through the creation of these ratios. So for each of the individual amino acids, we have a calculation for the ratio, which is the difference between the supply divided by the usage. So for the supply side, we also have the amino acids coming in from the diet, which are dependent on the ingredients. So, if you have a high lysine diet, you'll have high lysine in this equation. And then there's also the protein degradation. So we have muscle protein, which can be degraded and then goes into the amino acid pool. And that's also dependent on the various inclusion of this amino acids in muscle protein, for example. On the usage side, we have obviously the amino acids used for protein synthesis and those being oxidized. And so the whole kind of concept here is that we calculate each of these ratios and then we try and find the minimum, so the one that's the lowest. And if that is less than 1, which means that that amino acid is now considered the limiting amino acid, that's going to turn on our amino acid routine, which is going to trigger increased oxidation of amino acids. So for example here, I just have a regular simulation that I ran, and I ran it to be deficient in amino acid 8, which is lysine in this example. So you can see here that for this particular example, we have lysine is below 1 for the entire time. So that would trigger the amino acid routine. So on the left here, we have a little simplified flow diagram of the post-absorptive environment. So we have our amino acid pool. The inputs to this pool are through the dietary amino acids, which come from the absorption of either the milk replacer or the concentrates of forages from the small intestine. We also have inputs through the degradation of the various pools. So we have 4 main protein pools, which drive growth pretty much. We have the muscle protein, the high protein, the visceral protein, and the bone protein, and these are all able to degrade and add amino acids into this amino acid pool. In terms of outputs from this pool, we have obviously the synthesis of amino acids into these various pools, and also the oxidation of the amino acid to the acetyl-CoA pool. So in terms of the amino acid routine, how it works, we have a default equation which describes the flux from the amino acid pool to the acetyl-CoA pool. We also have a condition on this equation. So whenever the min ratio is below 1, this condition turns on, which results in increase in the amount of the amino acid oxidation. And what's really neat is that this equation is sensitive to the degree at which you have a deficiency in an amino acid. So for example, if you have a very severe diet in lysine deficiency, for example, you may have a min ratio of 0.8. You may also have a diet which is just barely deficient in lysine, which have a min ratio of 0.95, for example. And that very severe diet with a 0.8 min ratio is going to result in a higher level of amino acid oxidation compared to the very small and marginally deficient diet. So I think that's pretty neat. So anyways, yeah, ratio goes below 1. We see an increase in the amount of amino acids being oxidized. So more flux from this pool to the acetyl-CoA pool. That results in the concentration of those amino acid pool decreasing. And then our protein synthesis equations are based partially on the concentration of amino acids. So if that pool decreases, we'll see a decrease in protein synthesis. And so this ratio can kind of act as a feedback loop as well, which is neat. So if we see, a diet's deficient in lysine, for example, we'll see a decrease in protein synthesis. If the amino acid supply remains the same, for example, we see a decrease in protein synthesis. We're going to see a decrease in that amino acid usage, which is going to result in an increase in that ratio. So if it's 0.9, if we keep the model running for a couple hours, a couple days at a time, for example, that ratio will increase and actually turn that amino acid routine off. So it's pretty neat. Right. So I ran a simulation just to kind of show everyone how this works. So this is a 14-day simulation. For 3 days, which are shown in this red bracket here, I artificially decreased the amount of lysine in the milk replacer meal to simulate its efficiency. So you can see the amino acid ratio here. For lysine, it's above 1, and then I decreased the lysine in the diet. So we see this drastic drop for these 3 days. So the graph to the right is I just zoomed in on the graph to the left, and you can see the within day kinetics here. So we have 3 days, and we have 4 meals per day. So for example, over here, we can see when we have the milk replacer meal, we're getting an influx of that amino acid, which creates the ratio to go up. However, when that milk replacer meal is finished, the supply decreases. We still have some protein synthesis and things like that. The degradation of protein from the muscle pool to the amino acid pool is no longer enough to meet the requirements for synthesis. So we see the ratio goes down until the next milk replacer meal. So when that ratio is below 1, like I said, that turns on the amino acid routine, which increases the oxidation of amino acids, which is shown in this graph to the left. So we see increased oxidation, which results in decreases amounts of protein synthesis. Now, this is a very marginally deficient diet, so we don't see that big of a decrease, but it is there. So I wanted to kind of show how the model works compared to real life data. So I simulated a paper here. It's from 2012, and it's looking at the asynchronous supply of indispensable amino acids and how it reduces protein deposition in milk-fed calves. So basically, in this trial, they're feeding just milk replacer, no concentrates or forages, no solid feeds. They created this milk replacer to be deficient in both lysine and threonine by formulating a primarily wheat and whey-based diet. And from this basal diet, which was deficient in these 2 amino acids, they had 2 different treatments. The first treatment was called the synchronous treatment, and therefore they were supplemented L-lysine and L-threonine in all 4 meals. So they've had 4 meals a day. They're supplemented in these 4 meals, and so therefore all the amino acid requirements were met in this synchronous treatment. There's also this asynchronous treatment, so they were fed this basal diet, which is deficient in lysine and threonine. However, 3 of those meals, there's no supplementation, but that 4th meal, they supplemented the entire amount of those lysine and threonine supplementations into 1 meal. So a very big bolus for that 1 meal. So we have 1 meal where we have lots of amino acids and 3 where we're deficient. So how did the model react to this? So top left is the synchronous meals. So we can see this is the min ratio. So looking at the difference between supply and requirement. And so for the synchronous meals, we have no deficiencies. We meet the amino acid requirements. So therefore, the min ratio is always above 1. In contrast, we have the asynchronous feeding pattern, whereby 3 of the 4 meals are deficient and 1 is met, the requirements are met. And so you can see here that for 3 of the 4, we have the min ratio is below 1, which means that we are deficient. And then for that 4th meal, we have min ratios above 1. So whereby the requirements are met. So I want to compare the within day kinetics between what our model says is happening and what's happening in real life in this trial. So in the trial here, they measured leucine oxidation over the course of the day. So they had 4 different meals, and they measured the amount of leucine oxidation in 2 of the 4 meals. So for the first meal, this is when the asynchronous treatment is deficient. So we see in the asynchronous treatment, we see greater amounts of leucine oxidation compared to the synchronous because there is deficiency, so therefore those excess amino acids are being oxidized. Looking how it looks in the model, so it'll be this meal here, we see that the model is able to take this into account. So we're seeing more leucine oxidation, more amino acid oxidation for the asynchronous meal compared to the synchronous meal. And then we have the third meal over here. So this is the meal where we're supplying the asynchronous diet with a very large bolus of those synthetic lysine and threonine. We see the opposite kind of happened here. We see that we now have more oxidation with the synchronous compared to the asynchronous. And if you look at the meal pattern on this side, we see the same thing happen. We see that we now have more oxidation for the synchronous versus the asynchronous. And if you see here, there's this very drastic drop. In modeling, whenever you pretty much have discontinuation in your conditions, you're going to have these drastic drops. So just the way it is. It would be nice to have a nice continuous, nice continuous curve going down, but unfortunately, it's very hard to do sometimes. So looking at protein synthesis. So again, this is just the output of the model. We have the synchronous protein synthesis and the asynchronous protein synthesis. You can see here that when we're feeding the asynchronous, which is deficient, in 3 to 4 meals, we have less protein being synthesized compared to the synchronous meal, whereby all the requirements are met. However, with that one meal whereby we are supplementing lysine and threonine to meet the requirements, we see protein synthesis increase and is within the same amount as the synchronous meals. So they also measured nitrogen utilization efficiency between the 2 treatments. You can see here that with the synchronous treatments, we have higher nitrogen utilization efficiency compared to the asynchronous treatments. And that's obviously because in asynchronous treatments, in 3 to 4 meals, we are burning, oxidizing amino acids instead of depositing them for protein. So we'll have a less efficient cow. And then in terms of our model predictions, we can see the same thing here, which is very nice, that with the synchronous diets, we have much higher efficiency compared to the asynchronous diets. So far, this amino acid routine has been implemented successfully in veal calves. It's also used in swine in Vacuum University. So Walter Garrett's PhD student has applied it to swine as well. And so hopefully Anthony is able to use the same sort of framework to get it working in broiler chickens as well. So with that, I'm going to send it over to Kendra.
Kendra, we can't hear you. No. Yep. We'll just pause a moment for Kendra to come back. No, we can't hear you, Kendra. Kendra, we can always skip ahead to and do Jihao, and then you can figure it out if you want. Okay, I'm going to give Jihao control. Let him skip ahead. You got it, Jihao?
Okay, so can you hear me?
Yep.
Okay, yeah, I will start it from my part. Okay, so I will turn on my camera. Okay, so hello everyone. My name is Jihao Yu, and I'm a first-year PhD student. And I just got my second master at the University of Alberta in 2020. And my project is about using machine learning regression models to predict the palette quality. Oops. Okay, so machine learning refers to educating computers to perform specific tasks without explicitly programming them to do so. Machine learning is a subfield of artificial intelligence. It includes supervised learning, unsupervised learning, semi-supervised learning, and the like. Oops. Machine learning models and statistical models have two things in common. The first one is both of them focus on the same question. That is, how do we learn from data? The second one is both of them rely on the mathematics and probability. Compared with the statistical models, machine learning is less dependent on prior assumptions, and machine learning can be used to handle a large number of parameters with the presence of complex interaction. The most important thing is machine learning can be used for prediction. The palette quality can be affected by many factors like the moisture, the feed formulation. A previous study reported the effect of one or two factors on the palette quality. However, few studies investigated the palette quality by considering several factors. So my project aimed to investigate the effect of several factors on the palette quality by building machine learning regression models. It was hypothesized that features regarding manufacturing parameters, the feed formulation, and the environmental data would be useful to predict the palette quality. The preliminary data for the project were collected in 2020, and the manufacturing parameters and feed formulations were collected by Trial Nutrition. The environmental data, including the temperature, humidity, and pressure for the feed mill, were downloaded from the website. So there are 13 continuous inputs and 3 categorical inputs, and the output is the PDI. In this project, Python was used and 8 regression algorithms were applied. To evaluate the models, MAE, MSP, and the concordant correlation coefficient were used. And the MSP can be decomposed into the ECT, ER, and ED. And all error should be from the ED. This figure shows the permutation importance of features for all algorithms. As you can see, some features are more important like the bakery and the temperature, it means that these features are more helpful in prediction. Although the MAE of SVR was the lowest, the stacking regression had the lowest MSPE, the highest ED, and the highest concordant correlation coefficient. So this figure shows the linear relation between the predicted values and the true values. So all points should be on diagonal line, and the slope of the diagonal line should be 1, and the intercept is 0. So the stacking regression had the highest slope and the lowest intercept. So the conclusion for my project is the features regarding manufacturing parameters, the feed formulation, and the environmental data could be used to build machine learning regression models for predicting the pallet quality. And the stacking regression was the best model. The data for my project will be collected from September 2021 to December 2022, and we will work on 3 things. The first one is to improve prediction. The second one is to generalize the model. And third one is to apply the model in feed mills. In the end, I would like to thank Mafra and Troll Nutrition. Thanks.
Okay, now can you hear me? Bless.
You're good. We can hear you.
Awesome. Let's just, I guess, backtrack. I'll do the background for Gio's project. I can't go back.
You should be able to go back now. I see the little arrows. There you go.
Okay. All right, so back where we left off, sorry about that. We practiced it and it was fine, so I don't know what happened, but we're good now. So like I was saying, and you couldn't hear me, me and Jiha have a partnered project, my project feeding into his about pellet quality optimization at a mill level, and his project involves using the machine learning. So some background. So why do we pellet? So pelleting a diet has been shown to improve animal performance when compared with the same diet as a mash in both swine and poultry. So pelleting can increase feed intake, average daily gain, and feed conversion. These changes in ingredient composition and availability during the pelleting process can increase the palatability and digestibility of the diets. Alongside the seen increase in feed intake, diets are also more homogenized, meaning animals are more likely to receive the diet as formulated. So you're actually going to see those benefits that you formulated for at the mill and then at the animal level. So pelleting also greatly improves the physical characteristics of the feed, making it easier to get the feed from the mill to the animal's mouth. So pelleting increases the ease of handling a feed due to increased flowability and then increased bulk density. So feeding a low quality pellet can actually negate the benefits from pelleting. So pellet quality is often a very important factor to consider. So quality is typically defined by the ability of pellets to withstand fragmentation during packaging, transport, and handling. So it's to be fed without significant degradation and a significant proportion of fines. Pellet durability index, PDI, is often used as a predictor of pellet quality. So pellet durability index is measured by putting the feed through a tumbling box, agitating the pellets for about 10 minutes, and then recording the ratio of the remaining weight of intact pellets to the weight of the whole pellets before tumbling. And you typically want to see lots of pellets and less fines, indicating good durability. So my research. So I'm currently in my final semester of my master's, and my project is a meta-analysis of variables affecting monogastric feed pellet durability. So the objectives of my research, I aim to extract the data from literature and factors affecting pellet quality and analyze the data using statistical methods to detect patterns between pellet durability and formulation and the manufacturing factors, with the aim that optimized formulation and manufacturing strategies can be developed in order to increase the quality of pellets, improving animal performance. So I looked at over 300 models and analyzed the fixed effects for those models, and only 4 of them listed here had significant effects, explaining the trends in the data. So these are the lipid protein dihole model, the lipid dihole model, the protein dihole model, and the soybean meal dihole model. So dihole being the dihole diameter that the pellet gets pushed through. And then the effects and the significance are listed here. So these models were then evaluated based on their AIC values, the root mean square prediction error as a percentage, and then this value was then further decomposed into the error based off the overall bias, the ECT, the error due to deviation of the regression slope from unity, the ER value, and the error due to the random disturbance, so the ED value. The concordance correlation coefficient was also calculated to evaluate the reproducibility and fit of the results. So looking at these values, they're highlighted based off first and second best values. So the lipid protein dihole model and the lipid dihole model had the AIC values closest to 0, the CCC values closest to 1, indicating the best fits. Additionally, they also had the best measures of prediction and accuracy. The lowest RMSP value is in the lipid protein dihole model. It also had the majority of the root mean square prediction error attributed to random effect and not deviation due to regression slope or otherwise. So based on this criteria, you can kind of see that the lipid protein dihole model overall had the best fit, making it the most redundant and best fitting model. So looking at the factors that were included, so fat inclusion negatively impacted the pellet durability, and this may be due to the hydrophobic nature of fats, which can interfere with the steam treatment of the feedstuffs. So fats can partially encapsulate feed particles. This inhibits steam from penetrating the feedstuffs, preventing the gelatinization of starch, the denaturation of proteins, and that weakens the adhesion between the particles. So you'll see less durability. The presence of protein and soybean meal are kind of hard to separate, and they're likely due to the same effect, since a high soybean meal will likely result in a high protein diet. The heat and moisture applied during the pelleting process can lead to the denaturation of proteins. This will increase the pellet quality, since during cooling, the proteins will reassociate and new bonds can be formed, and that might be between different constituents, and these bonds can then strengthen and prevent degradation to fines. And then dihole diameter, the diameter used ends up affecting the final diameter of the diet. So it's not surprising that it was significant in all 4 models, given that the thicker the die, the thicker the cross-sectional area, and the more force is required to actually break apart that pellet. So the significance, it can be really challenging to predict the quality of pellets being produced due to the complex interactions between the ingredients in the formulation and the milling process. Predicting the effect of the interactions between the ingredients and determining the factors of influence to establish pellet quality can be really challenging. So this hopefully determining these factors can simplify that optimization process. So producers will be able to see improved economics through decreased feed wastage as fines, as well as the animal production benefits seen by feeding a higher quality pellet. And then poor pellet quality will also decrease efficiency and economics at the feed mill level. The production of poor quality pellets limits the economic potential. So increasing the throughput of the feed mill will produce more usable pellets each time the mill runs, which will hopefully make for better pellets and better money for everybody. So that then leads to Jihao's project. But we're going to skip through to Sarah.
All right, so everything looks good. Thank you, Kendra. So my name is Sarah Adams, and I began my PhD in September 2020, exploring the hybridization of artificial intelligence and mechanistic models to create intelligent precision nutrition models for next generation dairy production. So for decades now, the use of models has been the center to furthering our understanding of animal systems, where they generally have the objectives of optimally feeding and growing livestock. So as Jen mentioned, there are many different models that are used in animal science. So again, for example, we have empirical models that have been developed based on correlation, where we can use, for example, milk yield and body weight to predict feed intake. But with these models, we don't have a full understanding of the systems creating that correlation. And then on the other extreme, we have mechanistic models, which Vicky, Chris, and Anthony all described using in their projects. And with these models, we can gain a better understanding of how the system works, since they use a series of mathematical equations to represent biological pathways in the animal. So here, diving a little bit deeper into mechanistic models, the benefits of using them lies in their ability to improve our understanding of the underlying mechanisms of an animal's system. And that can assist in the movement towards precision nutrition, as well as the interpretation of experimental results. However, they are relatively slow to develop. They do generally require a large number of inputs, and a trained user is required due to their complexity. But now we have another tool to add to our list, and these are machine learning models, which Jihao is currently using in his project to predict pellet quality. So machine learning models are a subfield of artificial intelligence and relatively new to animal science. The use of machine learning models do have their advantages, and that's why we may be moving towards the use of them, including their impressive ability to identify patterns and make predictions or forecast tomorrow's performance from massive, noisy data sets. And then with the machine learning models, they are able to iterate towards the best model. And this is where mechanistic models may require a more manual approach when completing model evaluation. However, machine learning models do come with a number of limitations. So they have a tendency to overfit, where they learn the noise within the data set used to train the model. And this is a problem because the model may then perform poorly when asked to make predictions on new data sets. Next, these models require large data sets with large variability, so the models can learn as many foreseeable scenarios as possible. And finally, they lack transparency, in that it is not understood how or why the prediction is made, even from a mathematical point of view. And this is a huge disadvantage, and something that we may lose if we were to make the switch from using mechanistic models to machine learning models. So as I mentioned, machine learning and mechanistic models both have their strengths, but their optimal use in animal science may be a form of hybridization. So for my PhD project, I am exploring the means to hybridize machine learning and mechanistic models. So I hope to combine the machine learning model's ability to make really accurate predictions and have the possibility of being used by a greater number of people with a mechanistic model's strength of explaining causality or providing a better understanding of why they returned a certain outcome. And so the overall goal of my project will be to develop explainable artificial intelligence. So now you may ask, how am I going to accomplish this task? So in addition to the computer programming that will be required, this project is going to be largely driven by data. So luckily, there have been many recent developments in technologies that enable continuous monitoring and collection of individual cow and farm information. So these may include the use of sensors to collect measures such as body weight, methane emissions, milk production, feed intake, activity, and rumination, as well as we have additional sensors in the barn that may collect environment information or real-time environment data such as temperature and humidity. So for my project, I am fortunate to have access to two large data sets. So the first was provided by Chow Nutrition, and data was collected at their research facility, the Kempenshof Dairy Research Facility in the Netherlands. And the second is from the Ontario Dairy Research Centre here at the Elora Research Station. And then I will also be using the existing dairy rumen fermentation model developed by Dr. Jan Dijkstra and colleagues in 1992. So to explore hybridization of these methods, we will be using large amounts of individual cow data as inputs to the models. And then potential means to hybridize may include sequential hybridization, where outputs of machine learning models may serve as inputs to mechanistic models. So for example, dry matter intake predicted from a machine learning model may be used in a mechanistic model to determine the optimal nutrient composition of a diet. And then we also may have full hybridization, which may consist of having mechanistic models with parameters individually estimated by a machine learning model for each animal. And finally, we may be able to train biological knowledge into machine learning models by having a series of outputs from the mechanistic models serving as inputs to the machine learning models. And these are just some of the ideas that may lead us towards developing explainable artificial intelligence. And the outcomes that we will be focusing on include dry matter intake, milk yield, feed conversion ratio, and methane emissions. And so to conclude, the ability to develop more intelligent models that can improve our understanding for our decision making on farm by providing more accurate predictions, and this will aid in the movement towards precision feeding. And this shift, where diets are formulated to the individual rather than the group, can help lead to reduced feed waste with the ability to predict or to better predict feed intake, reduced feed cost by improving efficiency. It can help us work towards making dairy production more environmentally sustainable by being better able to predict a cow's greenhouse gas emissions or nutrient excretion into the environment, and improve our feed safety via traceability. And so I would like to acknowledge OMAFRA for funding the project, many professors at both the University of Guelph and Wageningen University, and Chow Nutrition for their collaboration on this project. And with that, I'd like to thank you for listening, and I will pass it back to Jen.
Awesome. Thanks, Sarah. So I'm cognizant of the time, and I've just got this one slide to kind of wrap it up. Hopefully we haven't given you whiplash from all the different topics, but I think it's really neat to highlight kind of the range of modeling methodologies that we can use and approaches that we can use to solve a variety of animal production problems and using modeling as a tool to increase our knowledge. You know, hopefully this will set us up well to kind of ride this digital wave in the future, to both support increasing our understanding, but also to support you know, our ability to take advantage of this huge data wave coming at us. With that, I'd like to thank my students for presenting, and we will take any questions that you guys might have.
Thank you very much, Jen and group of students. That was awesome. So yeah, I will reiterate Jen's request for questions. If anybody has any, even if you want to just type them on the chat, I can read them out, like if you're having difficulty with the sound. But otherwise, yeah, turn your sound on and just blurt out your question. You'll be fine.
I'll blurt out then. Chris, you know, I'm like obsessed with amino acids. One thing I was wondering, how would you put into that model? There's a lot of emerging evidence about the secondary effects of amino acids, such as improving immune function where it doesn't improve protein synthesis, improving metabolite synthesis when it doesn't improve protein synthesis. How would you factor that into the models the Simon model that you presented and explained extraordinarily well, although I feel like I could use an afternoon for you to, I probably didn't quite understand a few concepts of math that were applied in there, but how could you add those in?
So the big thing for Simon is the actual amino acids are only used for that routine. They're not used in any other way. So they're only used to calculate those min ratios, which result in increased oxidation, which results in decreased. So there's no other secondary systems that it's modeled at all. So it'd have to be a complete rewrite.
Do you see value in that?
Oh, for sure. Yeah, it's the main thing to me would be how big of an effect those things would have in terms of like going forward is if we see, you know, protein deposition or these secondary routines, do they increase in anything that's measurable with this model? Because in the end, this is a massive model. It's literally thousands and thousands of equations. It's crazy, and we can run for weeks and months at a time, right? So in the end, can we, if the factor is so small, can that be measured in the outcome of the model? Would be something that I'd look at first. If it makes sense to devote time to implement such routines.
Okay, so can I follow up on that a little bit? And mainly it's a nice segue because you said time for the routines. And then the other question I had was how you would factor in protein synthesis, not deposition, is a very acute response to that amino acid oxidation. And then over time, there's more of an accommodation of metabolism and a shift to try to salvage amino acids and protein. Can that be factored in as well, that time, the amount of time an animal is on a diet with differing ratios?
Oh, of course, yeah, you can do that. So right now, we actually have like a running average we use. So what that means is that when we feed a milk replacer, it's a very big spike right off the bat, right? But in reality, amino acids don't clear the blood instantaneous, right? There is some time that it stays and circulates. So to take that into account, we included, it's called a running average. So what it does is that it takes what happens in the past and takes that into account for your current value, which is a pretty cool thing. So if you're feeding, for example, right now it's, I think we have it set for a day. So if you feed a deficient diet for the milk replacer meal previous, and then you feed a diet that it has enough milk replacers, enough amino acids in that milk replacer, that deficiency in the previous diet is still going to be taken into account currently.
Okay, so I have, sorry, this is just fascinating. Great job, Jen. So does that also mean that you could start to develop one of the things that we always criticize in nutrition research is the effects of diets that the animal or the human has previously been on? So not amino acids, but is there a potential to be able to start to tease that out if you had, I mean, ag animals would be perfect, and frankly, dairy or beef would probably be optimum because you could gather so much data on those, and it's a lifetime data. Is that a potential as well?
I'm sure there could be ways to model that, but using the running average it's generally, it takes into account like a certain time period. So if you take into account like 14 days for that running average, everything that you have between that 14 days is going to be watered down, so to speak.
Okay.
So it's like it's an average that was happening at 14 days. So if you want to see if like you're feeding like a, you know, if you're going back a year, for example, and you're doing like a early life feeding regime and how that affects a year in the future, then the current running average will not do that. But I'm sure there's ways you could you could implement that. Like you could. Yeah, I'm not sure though, off the top of my head, how to do that. That's a pretty big question.
Really great presentation, guys. Really enjoyed it. Thank you.
Thanks, Kate. Any other questions? Well, I'll ask one myself here. I'm interested in everything you're doing here. It's really cool. I don't know, you guys have emphasized it, but the whole combining the machine learning and the mechanistic models, this is a really new area, you know, and the time is ripe. But I'm curious about the pellet quality model. It seems something new there as well in terms of who's the user going to be of the model. I'm curious, just out of maybe lack of knowledge of how it actually works at the mill. Are they ag engineers doing this? Are you guys creating also a new job for people, you know, to be designing the milling procedures and various things, you know, to get that pellet quality so that it's not crumbling on you and that kind of thing? I don't know, just.
Yeah, I don't know, Jiha, if you want to talk about it. I mean, certainly, so I think the target of the pellet quality model is to be applied in the feed mill. We've certainly worked with Trow, and I know they've revamped their data capture system actually to be able to automate capture of all of these additional variables, which are actually, you know, all of the data for it is being produced, you know, every feed run, but there was just no capture or retention of it. So actually in partnership with Trow, they've reworked their software, or they're reworking their software so that all of this data can be stored. And so the idea is eventually then such an algorithm could be used to, you know, predict kind of the nuances, because, you know, we've got all of these, like, you know, which was really interesting from Jihao's work, is the environmental temperature, like the regional temperature around the feed mill was one of the most influential factors predicting pellet quality. So being able to look at within this project of Jihao, kind of that interaction between the environment around the feed mill at the time of manufacturing, the feed ingredients, the nutrient content of the feed ingredients, and the feed manufacturing conditions, it's kind of optimally, you know, machine learning is kind of the optimal platform to really look at all of those interactions. And hopefully in the end, then the model can be applied in the mill to, you know, to optimize pellet quality given these complex interactions. I don't know, Jiha, if you want to say anything else there.
Yeah, I think in the future, I think the model can be integrated into a program, and people can use the program to predict the pellet quality. Yeah, so that is my idea, and we will work on it. Thanks.
Yeah, very cool.
Can I follow up on that, John? It's John Metcalf.
Yeah.
I'm assuming that the majority of that pellet quality stuff has been at steady state. But of course, as you change formulation and as you warm up the mill, those transition points are where you are going to be getting poor quality pellets and wasting or creating a lot of returns. So have you thought at all about how you might take account of that aspect?
Yeah, good question. Mark Malplatz, are you still on the call too? Because I think that with the new data capture system, we should be able to correlate when in the feed manufacturing run we take the pellet, the PDI sample. I'm not sure we have the capacity to take more pellet, more samples, but we certainly, you know, are going to be following the mill for a year. So potentially we should be able to correlate the time that the pellet quality sample was taken with the point in the run that it was taken.
Good. Any other questions from the audience? You guys have explained it all very well and very clearly. Blown everyone away.
Good job, guys.
Yeah. So, I recognize we've gone past time a little bit, sort of, and some people have moved on to other things. But thank you very much for the presentation, and it was eye-opening for all of us. The types of things that you can do with these techniques, and so I think people have probably gone away with some ideas themselves from that. And so, thanks again. And next month
we got Vern
Osborne's group.
Yep.
And so we'll send out a date and a link and everything in a short while, and see you all then.
Perfect. Thanks, guys.